to help you actually solve. So if I was trying to solve number 7, what would I do first? How can I undo the natural log?
You make it x equals e to the 3.4.
Good. I can do x equals, the base of natural log is e, that's our inverse, perfect, of 3.4, which that is just a number. So this is going to be our exact value. And then a lot of what we're going to do today is going to be exact values and decimal approximations. So at this point, you can just go to your calculator and do e to the 3.4, and it'll give you decimal approximation. This is approximately 29.9641. Okay. The first couple questions will actually have you just round to the nearest thousandths. But later on, we're going to do things to the 4th decimal place, so we'll do a lot of that. So another quick example then, if we were doing something like number 8, this again, natural log, so our base is e. X is going to equal e to the 1/2. Okay? And then you can get a decimal approximation on that as well. Okay? So that's the very first one. We're going to look at doing the transformations from exponential to logarithmic. And then we're going to do it the other way around, okay? This one will involve much more algebra. What do you guys think we should do now?
Subtract 5 first of all.
Excellent. Let's get rid of all the other stuff going on. Okay, we got to get our variable by itself. So we'll have 4 times e to the x minus 2 equals 65. Now where should we go? Good, so we know we're going to divide by 4, so we get e to the x minus 2 equals 65 over 4. Oops, 65 over 4. Okay. So then, what do you think we should do? Good, let's do the inverse. What's my inverse?
Log ln.
Natural log, because we had e this time. So we know that x minus 2 is going to equal natural log of 65/4. Good. Okay. That conversion step is actually going to be a very important property we're going to talk about a little bit later, okay? We can actually take the natural log or the log of both sides, and it allows this property where we can actually move this exponent out in front. But we'll talk about it a little bit more later, okay? So now at this point, we can just add the 2 over, and so your x value is the natural log of 65/4 plus 2.
And you can type on your calculator.
And this is just a number, so that's going to go, this will be the exact form. Now we have a decimal approximation, which, if we throw that in, we end up with natural log. Natural log is the ln button on the calculator. So we end up with 4.7881. Okay? Feeling okay with those?
Yes, sir.
Okay, so that's taking what you've done before break and applying it to solving, basically, right? We're going to get things into an exponential form, convert it to logarithmic, or have it in a logarithmic form, convert it to exponential. All right, so same idea here. Where would you go first with this one?
Add 5.
Good, we can add 5.
Divide by 3.
We'll divide by 3 next. And then from here,
X
Okay.
4 to the third
X plus 4,
to the third.
not quite, equals
Oh, equals e to the third.
e to the third. My base will stay with the base, so e to the third.
And then would you subtract 4?
Then we'll just subtract 4.
Remember the top one equals 8.
Oh,
Yes, 8.
yes it does. Haha. That was terrible. All right, that should be 8 because we added 5. Okay, which that's only going to change us by, this turns into 8/3 now. That is 8/3. This is 8/3. Okay, so our new exact answer, our correct exact answer should be e to the 8/3 minus 4. And then we can get the decimal approximation off of that. E to the 8/3 minus 4, 10 points something.
4.
Out of the fourth decimal place, we'll get 391. Okay. The reason we want to go to 4 decimal places is when you start doing, especially with logarithm stuff, little changes make a huge difference. And if you start only taking it like to the tenths, and then you do that a couple different times, and you have these rounding on rounding on rounding errors, you start to go from like 10.4 to like 10.3 or 10.2, which may not be a huge difference, right? Unless you're talking about like trying to connect an airplane wing or something. And now all of a sudden you're 2 inches away from making your airplane wing connect and you can't fly anymore. Okay? So rounding on rounding errors can sometimes get us in trouble. So anyways, that's similar to what we just did on the other one. Gotta get the variable by itself and then use the inverse to undo them. Okay. Here comes a couple new properties. You may have seen this before, especially I think if you were in Algebra 2 Trig last year, you've probably seen this. Otherwise, this may feel fuzzy and come back to us a little bit. One of the properties we're going to look at is if you have the natural log of A plus the natural log of B, there's a trait that we use where we can combine this into a single term and call this the natural log of AB. Okay? So if we're going to add 2 logarithms together, you can actually combine that as one logarithm where you multiply their insides. And then if it's subtraction, then we would use division instead of multiplication. Okay, so for example, on 27 here, we could combine this as the natural log of 2x times x minus 7. Okay. And then you'll just distribute that through. So this becomes the natural log of 2x squared minus 14x. So we can combine these. Just for the sake of seeing an example with subtraction, let's pretend that this is actually subtraction. So this is going to turn into the natural log of x plus 2 divided by 3x. If you can simplify it, go ahead and reduce it. If not, you can leave it as just a fraction that's not reducible. Okay. Okay, so that's one of the first properties we'll look at, is this addition and subtraction thing. You can combine them. Then we're going to take that information and work backwards with it also. And what I mean by working backwards is now they're going to give you something where they want you to take, oh, just kidding, this is our next property here. Here's the other property that I told you we'd come back to. So there's a really cool property, and why we love logarithms. It helps us so that we can actually solve for something with a variable in the exponent. If you take the log of both sides, or if you have the log of something, you can take its exponent and move it out in front. So this thing's allowed to just come out front. That's part of its properties. And if we think about, for example, we looked at, what was the one we looked at? It was like natural log of, what was that one? Let's just say we had natural log of 4, oops. What did we have? What was the one we had? Now I'm forgetting the example we just looked at. So let's say we had the natural log of 4x equals 3. Okay. How would we have solved this? We would have done that inverse thing where we said, okay, so our 4x equals e to the 3, right? So if we think about that step, oh, now I'm working the wrong way. I just totally butchered that, didn't I? All right. So if we look from going from this step to the other step, essentially what we're looking at is you could take the natural log of both sides. So if we took the natural log of both sides, basically. Okay. So this turns into the natural log of 4x. And this becomes the natural log of e cubed. Okay. Then we can apply this rule to it, basically. So it allows that 3 to move out forwards. So you can say that natural log of 4x equals 3 to the natural log of e. Anybody remember what natural log of e is? 1. So this just disappears, and sure enough, we end up getting right back to where we were. Okay? So that's why that property works. So when we look at that converting between exponential to logarithmic forms, if you were to actually take the log of both sides, you can actually work back through it and get back to the original exponential form or logarithmic form. We can work back and forth. So that's where this property comes in. And so all you need to actually do for these ones, it's a very straightforward basic one, is you're going to grab this and say that this is x plus 2, that exponent, times the log of 8. And so that's all we're doing. We're just applying this very basic property that allows us to move things out front. Okay, so something like number 45 or 44, you would just grab that quantity and you can move it out front. So this becomes the quantity x minus 3 times log of 15. Okay. So that's one of those things that will help us actually solve a lot of things that aren't quite as nice, things that have weird bases and stuff like that. So, all right. Now I think the last piece is the expanding back out. Okay, so we kind of looked at the idea that if I have two logs added together, that we could multiply them internally. Now we're going to take things that are already as one log term and expand them out so they're basic log terms. So I can take something like this where this is basically just multiplied together. So this will turn into log of a cubed plus log of b. And so now we've undone the multiplication step there by going to our property where we can add them, add two different logs. And then we can apply that last property we just looked at and move the exponent out front. So this can be written as 3 log a plus log b. Okay. So today, for the most part, we're going to do a little bit of solving with some of that converting between exponential and logarithmic forms. And then we've got 3 new properties kind of that we're looking at. So a quick summary of all that stuff. I don't know if it'll actually fit. Oh, sweet, it fit inside my screen. Okay. is this. So our exponential and logarithmic properties, going from logarithmic form to exponential or vice versa, that's kind of our base foundations. That's stuff we did before break. Today we're looking at the idea that if you have a log of something with an exponent, you can move that variable up front. So these are equivalent to each other. And then we looked at if you add two logs together, you can write them as a combined single term. And then if you subtract, you can combine them as a single term but with division. And then lastly, I just want you guys to make sure we remember log base 10 equals 1. Those are the inverses of each other. Natural log of e is 1. That's the inverse of each other. And then I just threw in a complicated example. So log of a cubed to the 4th root of b. You can expand that out. You can expand that out so you've got 3 log a plus 1/4. So fractional exponents, those are the same as roots. So remember that if you haven't seen that in a while. So that would be to the 1/4 log b.